All right, everyone, here we are for part 2 of the video lecture for chapter 13. We'll finish this up here in the second video lecture, or part 2 rather. So at the end of the previous video for this chapter, I was talking about the z-score calculation for an individual measurement compared to the z-score calculation for a sample mean. And the idea there with that last slide was to show you that a single measurement has far higher probability of occurring, especially further away from a mean, than would a sample mean of occurring. So if we have a population distribution, a single value far away from the population mean is more likely to occur than a sample mean of, say, 5 individual measurements of the same value occurring on that population distribution. That's because individual measurements are much more variable than averages or sample means, all right? Okay, so with this slide here, we'll look at that again, just with a different example. So let's say that we have a normal population with a mean of 15 and a standard deviation of 3.5. Again, this is how we would state that in statistical notation, okay? Normally distributed, mean of 15, standard deviation 3.5. Now, what is the probability of a single measurement, okay, x value, of less than or equal to, let's say, 7.8? Well, look down here. This blue line is our frequency distribution, our density curve for this population, right? Notice your mean up here is, or your standard deviation is 3.5, and your mean is 15. Okay. So on that blue curve, population curve, how likely is it for a measurement of 7.8 to occur? Well, and still I didn't do my formula here, so let me fill that in real quick. Okay, so z equals x minus mu over our standard deviation. So we plug in a value of 7.8 for x, subtract from that our mean of 15, and divide that by our standard deviation with a population of 3.5, and you end up with a z-score of minus 2.06. Here's the calculation. So you look up minus 2.6 on the table, table B. Area to the left ends up being 0.0197, or 1.97%. That makes sense because we're talking about roughly 2 standard deviations, and 2 standard deviations plus or minus from the mean should cover 95% of our area, right? So you'd have 2.5% on either side, outside of 2 standard deviations. Okay, so that's a pretty low probability of occurrence, but it's one measurement, so it could happen. Now, what about a sample mean of 7.8? Right? What's the probability of a sample mean of 7.8 or less? So let's figure that out. So let's say we have these 5 measurements here now, right? Well, here you see their individual z-scores, okay? But what if we average these as a sample and get a mean of 7.8? Well, now, because we have 5 measurements, right, we're going to take into account the sample size in our z-score calculation. So let me fill this in again. So z equals now our sample mean minus our population mean over our population standard deviation divided by the square root of n. Key point here, notice that's a sample mean, whereas this is an individual value, right? If you're dealing with individual measurements, you're dealing with a population distribution for the z-score. If you're dealing with means, you're dealing with the sampling distribution for the z-score. So we correct the population standard deviation by dividing it by the square root of the sample size. All right, so now we would take a mean of 7.8 minus population mean divided by the population standard deviation of 3.5 over the square root of 5, a sample size of 5, all right? Now you do that calculation, and you end up with a much lower, or much higher z-score actually, in terms of absolute value, minus 4.6. Why? Well, now look at our sampling distribution curve. That's the red dashed line. So you see it's more narrow because we have a smaller standard deviation defined this way, and where would 7.8 fall as a mean? way over there. I mean, if you zoomed in on this, you'd see there's a little sliver of area to the left of 7.8, but not much. How much is to the left of it? That. Convert that to a percentage, multiply by 100, 0.00021%. So whereas an individual value of 7.8 would have a roughly 2% chance of occurring on our population distribution, a sample mean of size 5, the mean of that, 7.8, would have a far less chance of occurring because our sampling distribution is more narrow. All right? Okay. And again, the reason for that is because having all of these x values here, okay, in a sample falling right over there as they would, look at their values, right? They would have to fall right over here. The chance of taking 5 individual measurements and they all fall over here is extremely rare. How rare? 0.00021%. All right, so this brings us to talking about what we call the central limit theorem. So whenever we are randomly sampling from a population with a given mean and a given standard deviation, if our sample is large enough, the sampling distribution of the sample mean will be approximately normal. And this is how we would define that sampling distribution, okay? So the point here, in layman's terms, is that even if you have a skewed population distribution, if you take a large enough sample from that, the sampling distribution for that sample will be normally distributed. That's a really important point because a lot of statistical tests, as you see right here, assume normality for the sampling distribution. If you can't sort of illustrate or show that your sampling distribution is normal, then there are a lot of statistical tests that you can't run on the data set that you're dealing with. Okay, and so this is why you have to sort of check your data. We're going to see more about that here in the next couple of slides. So, another point about this, right? In addition to a larger sample giving us a more normal sampling distribution, a larger sample will also give us a better approximation of normality, okay? Also, as we'll see, the larger the sample, the more likely it is that the sampling distribution mean will match the population mean. That's a key point as well. Okay, so if sample size is important, the question is, how large of a sample do you need? Excuse me. Well, there's no hard and fast rules on this. All we really have are guidelines, okay? And these are 2 guidelines here that are important. You should remember these. So a sample size of 25 or more is usually large enough to give us a normal sampling distribution, even from a skewed population, okay? Now, not wildly skewed, let's say mildly skewed. And you can have a few mild outliers in that, but if you have a mildly skewed population distribution with a few mild outliers, if you get a sample size of 25 or more, then you're probably good. You're probably going to have a normal sampling distribution. Now, what about a sample size of 40? Well, this will typically be good enough to give you, or to help overcome extremely skewed population distributions still with mild outliers, all right? Okay, so let's take a look. So here on the left, we have a population with I would call a wildly skewed distribution. This is a population distribution, wildly skewed, all right? So let's say we took, 1,000 samples from that population distribution, each one consisting of 2 measurements. So 1,000 samples, each one of size 2. We would have 1,000 averages, right? So you plot those averages. Okay, so for example, 1 sample of 2 measurements, you average those 2 measurements, plot that mean. Do that for all of the other 999 as well, plot those means, and you get a sampling distribution that is still relatively skewed, all right? What about sample size of 10? So 1,000 samples of size 10 each, plot those 1,000 averages, you get a more normal distribution. Still a little bit of skew, but not much. 1,000 samples of size 25 each, plot those averages, and you see you have a normal distribution. So this is, again, central limit theorem, right? That's what this is showing us. This is why sampling works, and it's why we always want to have the largest sample size we possibly can, okay? All right. So What if we don't know, however, what our population looks like? What if you don't know the population distribution? For example, can you measure all 7.3 billion people, their heights? No, you can't, okay? So we don't really know what that might look like, right? Well, if all we have is sample data, then all you can do is plot the frequency distribution for your sample, okay? So here we're talking about basically a single sample. So let's imagine we have a single sample, okay? And we don't know if it came from a normally distributed population or not. Take that single sample and plot it on a frequency distribution, so a histogram. Look at the histogram for that single sample with all the individual data points plotted on that histogram and describe its shape. The shape of that single sample histogram should give you an idea of what the population distribution looks like, okay? All right, and that's this point right here, okay? So the central limit theorem then can also help us to figure out whether the sampling distribution would look roughly normal or not. So for example, you have a population, you don't know if it's skewed or not. Take a single sample from it, you plot that, and you get a skewed frequency distribution. That single sample frequency distribution, the histogram, is probably going to tell you that the population distribution is skewed as well. So if you know it's skewed, then you probably want to have a sample of, say, 40 or more in order to ensure a normally distributed sampling distribution, okay? And that's why this is important. So let's look at some examples. So here we have angle of big toe deformations from a single sample. This is 38 patients. They plot each individual patient's frequency on this histogram, and you get a roughly normal distribution. That right there tells you that your population distribution is probably normal as well, okay? So you wouldn't necessarily have to have a very large sample size to ensure that you're sampling from a normal sampling distribution. Okay, 25 might do it. All right, but here in this next example, again for a single sample, we have 74 adolescent girls. They've looked at asked them how many servings of fruit they eat per day. So we see that this is wildly skewed, isn't it? It's highly skewed, all right? Well, that tells you that your population is probably skewed as well, and so you probably want to have a sample size of at least 40 or more to get a normal sampling distribution, so that you can do these other statistical tests which assume a normal sampling distribution. That's why this is important. You don't know what your population looks like, take a single sample, plot the frequency. If it's normal, then smaller sample sizes are probably okay. If it's skewed, you're going to need larger sample sizes to ensure that you're sampling from a normal sampling distribution, all right? Okay, another example. Atlantic acorn sizes. So here we have a single sample of 28 acorns. It's wildly skewed. I mean, massively skewed, right? So let's describe that distribution. Skewed, as I just said, okay? So what would be the shape of the sampling distribution, let's say, for samples of size 5? Well, you know it's going to be skewed, all right? What about samples of size 15? Because this is so skewed, that's still going to give you a skewed sampling distribution. What about samples of size 50? Well, now you're probably going to get something more normal, all right? So that's why this is important. A single sample will tell you a lot about what the population looks like. From that, you can judge how large of a sample you need to get a normal sampling distribution. Okay. Last thing to talk about in this chapter is what's called the law of large numbers. So the law of large numbers says that as the number of randomly drawn observations increases, in other words, as our sample size increases, the mean of the sample mean gets closer and closer to the population mean. This is just a way of saying that our sampling distribution mean will get closer and closer to the population mean with larger and larger samples. Again, another reason why large sample sizes are important. We can do this with, for example, quantitative data, where we're measuring maybe blood alcohol levels or cholesterol levels or whatever, anything you can measure. We can also do it with categorical data that we convert to proportions, right? Number of males versus females or something like that. So it works with proportional data, and it works with quantitative data. Okay, so what are you seeing here? So let's say we have number of observations here on the x-axis, all right? This is our sample size. And we have the mean of the first n observations on the y-axis. This red line is a moving average. So our first measurement might be, what, 28 right there. Okay, we can't have a mean of one number, so that's our actual first measurement. Our second measurement is then included with the first measurement and the average calculated, and this new peak is our new average. Then we include a third measurement and calculate a new average. Fourth measurement, calculate the average again. Fifth measurement, calculate the average again. This is a moving average, right? Every time we change the average, we're including one more data point and re-averaging. And you see that with larger sample sizes, the sampling distribution average approximates or gets closer to the true population average of 25. Okay, so this line will get closer and closer and closer to our true population mean at larger sample sizes. It also works with categorical data or proportional data as well. Now, there's an applet for the law of large numbers on Canvas. Okay, so you can go there and kind of play around with this and you can see how it actually works. All right. Okay. So, to summarize then, when sampling randomly from a given population, the law of large numbers describes what would happen if we took samples of increasing size n. That was the previous slide, right, with the moving average line. A sampling distribution describes what would happen if we took all possible random samples of a given size. It describes the shape of the sampling distribution based on the sample size. Again, larger sizes, sample sizes, will give us more normal sampling distributions, okay? All right, so all these concepts here in this chapter are really important as we move forward into the next few chapters, which are all about hypothesis testing. Okay, everything we're going to talk about in hypothesis testing assumes, for the most part, that we have a normal sampling distribution. And understanding sampling distributions then is why chapter 13 is so